Hey everyone, so today I want to cover this density problem, which will hopefully be helpful in understanding how tension and mass and volume play in doing these calculations with like fluids. And so in this problem we have three boxes, A, B, and C, and we can see that box A is tied up to the bottom of the container with a string, box B is just floating in the middle of the liquid, and box C is tied up upwards. And so they're all in equilibrium, they're not moving, but we want to figure out what their densities are. And we're given some extra information. So for example, we know that they have the same exact volume, so that's important. We know that the liquid or the fluid has a density of 1,000 kilograms per meter cubed. We also know that the buoyant force on box B is specifically 20 newtons. And we also know that the tension in both strings is 8 newtons. And so let's just begin by considering the buoyant force. So the buoyant force is a force, so that's good, which is given by objects being within water. And so it's mathematically given by the density of the fluid, so rho f, times the volume displaced within the fluid, times gravity. And so we can do a check here and see if the units make sense. So here we have density, which has units of kilograms per meter cubed, and volume has units of meters cubed. And so we can see that these volume units will cancel out and we'll just be left with mass. And mass times gravity, or the acceleration due to gravity, gives us a force, ma. So we can see that it's a force, so that's good to know. And in this case, the important thing to note is all these boxes are fully submerged, which means that the volume displaced is going to be exactly equal to the volume of the boxes. And this is because it's fully submerged, but you might imagine some cases where it's only partially submerged. And those problems have like different problem solving approaches. But in this case, we can safely say that the volume displaced, Vd, is equal to the volume of the boxes. So that'll be useful. So, okay, let's begin solving this problem by considering the middle box, box B. Because it seems like the simplest one. It doesn't have any strings, so it's just floating around. And so let's just draw a free body diagram. We're on Earth, so it's gonna have some gravity, so some weight, mb, I'll do capital B, mbg, and it's also gonna have a buoyant force, fb. And so if we set up to be our positive coordinate, then what we can say is fb minus mb g is equal to 0. And what we can do here is we can just rearrange. We can get fb equals mbg, and we want to find what the density is. And so we're going to rewrite the mass in terms of its density, and we can always do this. So I'll call this rho b, which is what we want to solve for, times the volume of the box. And in this case, I'll just call it v for the volume, because it will be the same for A, B, and C. So we have this, so I'm going to go back here, and I'm also going to rewrite the buoyant force in terms of what it's actually equal to, which is the density of the fluid times the volume, and notice the volume displaced is equal to the volume of the box, so I'll just leave it as V, times gravity equals, and in this case I'll replace it with our density equation, rho B, V, G. And so we can see that V and G nicely cancel, and so we just get rho F equals rho B. But remember that rho F is 1,000 kilogram meters cubed, so it's something that we know, which means that rho B is just equal to 1,000 kilograms per meter cubed. And this is a useful result because it actually tells us that if you have an object that's not attached to anything, it's just floating in like water, for example, if it's just staying still, the density of that object must be exactly equal to that of the fluid. So this is an interesting result, and it's useful to keep in mind. And so I'm going to keep it in the corner of this page. So let's erase this. Let's move this over here. So we've already solved a third of the problem. So that's nice. So now let's go with A. So box A, let's just draw the free body diagram. We're going to have two forces here, or actually we're going to have three, right? Because, okay, we're still on Earth, so we're going to have some weight. It's going to be MAG, and we're also going to have a buoyant force, as before, FB. And something to note about the buoyant force is is that you may have already noticed that, it just depends on the density of the fluid. That's not changing. It depends on gravity, which is a constant. And here, it depends on the volume displaced. But again, they all have the same volume, and they're all submerged, which means that every one of these boxes is actually going to have the same exact buoyant force. So that's going to be useful because we're going to be able to use that fact when we're analyzing the physics of this. So we have FB, MAG, and the force that we have to account for now is the tension, which comes from this string over here. And so that's just going to be an arrow pointing down. I'll call that T. So again, let's say that up is positive. You can make it down positive. It'll all work out. I'll say up is positive. And so we'll get that FB minus T minus MAG is equal to 0. Great. And we can just replace stuff here. So we can say that FB is equal to 20 newtons, because again, the buoyant force is equal for all of them. And we know that for the box B, it was 20, so it must be that for everyone. So 20 newtons minus, we know that the tension for both strings is 8 newtons in magnitude, so we'll just write that, 8 newtons. And I'll just move this MA to the right, so MAG. Perfect, the left side gives us 12 newtons, and the right side, I'm going to rewrite in terms of its density, because again, that's what we're solving for. So I'll write rho A times V, which again is the same for all boxes, times G. Okay, so what can we do now? So in theory, we know what G is, and we know that V is the same for all of them, but we don't know what it is numerically. And so here is a trick that we're going to do. You could in principle use an argument from ratios and sort of like say that, the density was like 1,000 for this, and we can compare the forces. But I think maybe like a more sort of brute force, but I think clearer approach is the following. So let's find the volume of all these boxes. And so we're going to go back to our density problem here for box B, and recall that we had, before for box B, we had FB equals rho B times G, right? So we had the buoyant force was equal to, and I forgot the volume. There we go. So we had that the buoyant force was equal to, in magnitude, to the weight of box B. And the reason why I'm bringing this back is because what we can do here is we can say, okay, we know the buoyant force is 20 newtons, and we now know that the density of the block is 1,000 kilograms per meter cubed. And so what we can say is, and we have VG here, so let's just solve for V. We can do 20 over 1,000. We can include G there, because we're also dividing by G. This is going to be equal to our volume. And so if we do this, we can just go, we can just plug this expression, because it's just a volume, into our expression here. And so we're going to get 12 newtons equals rho A, and then our volume expression is 20 over 1,000 G times G. And I didn't write G as a number because they cancel out here, which is nice. And so we're just left with 12 newtons, and now let's just solve for rho A. So let's just multiply by 1,000, so times 1,000. I'm being a little bit messy with the units here, but hopefully it's okay. Divided by 20. And if we do this, if you run the numbers, you'll end up finding that block A has a density of 600 kilograms per meter cubed. And so the crucial thing to understand here is that I used my result from block B, knowing the density of the block and the buoyant force associated with it, and I found what the volume had to be. And since the volume is the same for all the boxes, this allowed me to solve for the density in block A. And so, awesome, let's just put this result over here. So rho A equals 600 kilogram per meter cubed. And we can see that it's less than that of block B. Perfect. So we're almost done. We're just missing one more block. So let's erase this. Perfect. And so now let's consider block C. So block C is very similar to A, except now we have, we still have, well, it's a wonky box. Let's see, let's redraw it nicely. Okay, one more try. One more try. There we go. So we're still on Earth. We still have M, and in this case, I'll call it MC G. We have a buoyant force, which again is the same for all of them. And in this case, the tension is going up because the string is pointing up. So we're going to have our tension force up here. So let's just do some analysis. So we have the positive going up. So we'll have FB plus T, because again, they're pointing in the same direction, minus MCG equals 0. 0 because they're in equilibrium. Okay, so let's get started. So the buoyant force is the same for all boxes. This means that this is 20 newtons. The tension is also the same, so we're going to have plus 8 newtons of tension. This is equal to mcg. The left-hand side is just 20 plus 8, so we're going to get 28 newtons. The right-hand side, we're going to write as densities. So we're going to get rho c, which is what we want to solve for, times the volume, which again, we solved for before, times g. And so now that we know the volume, we can just plug it in here. And I erased it, so let's rederive it. So recall that we had FB equals MBG for the B box. We have 20 newtons here. We have rho B, which is 1,000, so I'll just rewrite that here, times G. And we also have V here. So we're going to solve for V. We're going to get 20 over 1,000 G. So this was our expression for V. I'll make the G a little bit more clear because it looks like an 8. So let me just grab this. We're going to put G here. Awesome. So let's just plug it in. So we're going to get 28 newtons equals, and then rho C is what we want to solve for. V is 20 over 1,000 G. And again, G nicely cancels out. So now we can just multiply both sides by 1,000. We'll get 28 times 1,000, divide by 20. And if you do the math nicely, you're going to get 1,400 kilograms per meter cubed. And so this is our density C. And so this is how you approach these problems. I highly recommend being sort of organized with all your things when you're dealing with these problems. But I think that the main lesson, or one of the biggest ones, is when you have a block that's sort of floating within the liquid with no strings attached or anything like that, then its density must be equal to that of the liquid. And although you might sometimes see people solve these problems using ratios, like comparing sort of like the force each block experiences and stuff like that, I feel like that's not as clear as sort of solving for the volume directly. And so this will work if you have the information. And yeah, feel free to ask like any questions about this. And yeah, I hope this helped. Thank you.